Welcome back to the channel. Today is a special day because today I'm finally showing you the full picture of something I've been building for a long time. This is DOMIX, my completely open source DIY modular home automation system. And yes, it fits right inside a standard electrical cabinet on a DIN rail, just like a professional building automation system. So what exactly is DOMIX? At its core, it's a centralized smart home controller that I designed from scratch. PCBs, 3D printed enclosures, firmware, everything. No cloud, no vendor lock-in, no black boxes. Just a system that you can understand, modify, and expand exactly the way you want. The philosophy behind DOMIX is simple. Centralize all the logic inside a dedicated control cabinet. Wire your inputs buttons, contacts, sensors, and your outputs relays, actuators, valves all back to one single point. One brain, one place to debug, one place to expand. Let me walk you through what makes DOMIX tick. The system is built around a family of DIN rail modules, all connected through a shared I2C bus. Every installation starts with the M1 core module. This is the heart of the entire system. It runs an ESP32 S3 microcontroller, has native Ethernet via a W5500 chip, a Zigbee radio for wireless devices, an RS485 interface for field sensors, and a small OLED display on the front panel. Then, around the M1, you add only the modules you actually need. Need digital inputs and outputs? That's the M2, door and window contacts, M3. 6 relays for boilers, pumps, and HVAC, M4. 12 relays for blinds and shutters, M5. Want to monitor your energy consumption with clamp meters? M6. Pure outputs, M7. Pure inputs, M8. Garden irrigation with 24-volt valves, M9. And then, going beyond the cabinet, there's a family of room sensor nodes, the S, S1, and S2 modules. These are standalone boards that mount directly on the ceiling or inside a standard wall box, and they pack a serious sensor suite: millimeter wave presence radar, CO2, VOC, temperature, humidity, light, and even an IR transmitter to control your air conditioners. They talk back to the M1 over RS485 with Modbus RTU. The whole system is programmed with ESPHome, and every single schematic, firmware file, and 3D model is open source. This is not a product. This is a research platform, built for fun, built to learn, built to share. Before we dive into the build, a quick word from this video's sponsor, Oshwalab Stars 2026.
$85,000 prize pool. The Easy EDA 2026 Stars competition is now open worldwide. Material costs largely reimbursed. $100 JLC coupon for every qualified completed project. Top 28 engineers get invited to JLC Factory to see production up close. No pitch decks, no fluff, just working hardware. Submit your build now.
DOMIX is part of the Oshwalab Stars program. The link is in the description if you want to check it out. Now, let's get into the build. Every DOMIX module is made up of 3 stacked PCBs, a lower board that carries the core electronics, a vertical board that handles mechanical and electrical interconnection, and an upper board for the user interface, whether that's LEDs, a small display, or physical buttons. All boards were ordered through JLC PCB and the components from LCSC. For reference, the total cost to build all modules from scratch comes in at around €420. And that includes the 3D printed enclosures, consumables, and stencils for solder paste. Not bad at all for a system of this complexity. The M1 module comes in 2 hardware versions. Version 1.0 exposes 2 I2C buses directly from the ESP32 S3. Version 1.2 adds a TCA ESP9548AI2C multiplexer that splits the bus into 8 independent channels. This is the version you want if you're planning a larger installation. The expansion modules, M2 through M9, use I2C expander chips like the PCA9535, PCA9554A, and PCF8574. Each one has a DIP switch or solder pads to configure its unique I2C address on the bus. This is critical. No two devices can share the same address. Before assembling anything, I always build an address table first. The relay modules, M4 and M5, use N-channel MOSFETs to drive the relay coils from 5 volts, keeping the 3.3 volt logic completely isolated from the switching side. The contacts themselves can handle up to 10 amps at 250 volts AC. So yes, you can connect your boiler's 230 volt control circuit directly to the M4 relay contacts, but always, leave that work to a qualified electrician. The M6 energy meter uses a ZMPT101B voltage transformer and a CD74HC4067 analog multiplexer to read up to 10 current clamp inputs, all converted through an ADS1115 ADC. It gives you real power monitoring, not just current estimation. The Sensor S core board is built around a Raspberry Pi RP2040 with 16 megabytes of external flash, a MAX 13487 ERS485 transceiver, and USB-C for programming. The daughter boards, S1 for the ceiling, S2 for the wall, carry the actual sensors. Everything communicates back to the M1 via Modbus RTU over RS485. All the enclosures for the DIN rail modules are fully custom designed and 3D printed. The dimensions follow standard DIN module sizes, 2 or 4 modules wide depending on the board, so they fit perfectly in any standard electrical panel. The wall thickness is 1.5 millimeters, thin enough to print quickly, solid enough to handle. I printed everything in eSun PLA+, which gives a great balance between rigidity and ease of printing. Each enclosure uses threaded brass inserts heat-pressed into the plastic and M3 screws to clamp everything together. The DIN rail clip is identical across all modules. Just press in, lock with a flat screwdriver. The front panel is the fun part. For the colored graphics and labels, I used a multi-material printer with at least 2 filament colors. The trick here is to print the front face down, so the graphics face the build plate. It takes a bit of tuning to get the layer adhesion right at that scale, but the result is clean and professional looking. If you don't have a multi-material setup, no problem. There are also blank front panel files included in the project with no graphics or cutouts. The connection label plates are printed at just 0.4 millimeters thick in 2 colors, with the text facing upward. They snap into the front panel and make it easy to identify every terminal in the cabinet at a glance. For the sensor nodes, the ceiling S1 enclosure is designed for flush mounting. It sits flat against the ceiling with precise openings for each sensor and the IR window. The S2 enclosure fits directly into a standard 503 wall box, the same box used for light switches, which makes it incredibly easy to retrofit into existing rooms. Assembly is straightforward once you have all the parts ready. Each module snaps onto the DIN rail, and the modules are connected to each other via a flat IDC cable, an 8-pin ribbon cable with IDC connectors that you crimp yourself to exactly the length you need. I specifically chose IDC flat cables over pin headers for a few reasons. Pin headers are fragile in tight cabinets. One wrong movement and you bend a pin. Flat cables are much more forgiving, easier to route, and easier to disconnect one module at a time without disturbing the neighbors on the rail. Each module has 2 IDC connectors, so the bus daisy chains from module to module in a multi-drop configuration. Power, 5 volts, 3.3 volts, ground and all I2C buses, travels on the same cable. For external connections, every module uses screw terminal blocks with a removable plug. So you can pre-wire the terminal block, then just plug it in. Each terminal accepts cables up to 1.5 square millimeters. The M1 also has dedicated connectors for the Ethernet cable, the RS485 bus to the sensor nodes, a one-wire header for DS18B20 temperature probes, and an SMA connector for the Zigbee antenna, which I recommend running outside the cabinet on a short extension for better reception. The 24-volt AC supply for the M9 sprinkler module is the only external AC power that enters the DOMIX cabinet directly. Everything else runs at 12 volts DC maximum. With the hardware assembled, it's time to bring it to life. The M1 runs ESPHome on the ESP32S3. The firmware is structured around a single entry point, main.yaml, which acts as a manifest. You simply include or comment out the packages corresponding to the hardware you've actually installed. Don't have an M9? Comment out that line. Done. All the configuration parameters, IP address, MQTT broker, I2C addresses for each module, live in a single file called data.yaml. You edit that one file and everything else adapts. It's a clean, declarative approach that I really enjoy. The M1 supports two I2C bus configurations depending on your board version. With version 1.0, you get two direct buses from the ESP32. With version 1.2, you activate the TCA 9548A multiplexer and get 8 independent channels, which means far more devices with no address conflicts between channels. Each sensor node runs its own ESPHome firmware on the RP2040. The S firmware exposes all sensor readings as a Modbus RTU slave: temperature, humidity, pressure, CO2, VOC, light, presence, and more, all mapped to well-defined registers. The M1 polls each sensor node every 5 seconds and publishes everything to MQTT. The MQTT topic structure is clean and consistent. Every entity follows the pattern: device name, module name, channel name, then either state or command. Any MQTT-capable automation platform picks up every entity automatically. No manual configuration needed. The first flash is done over USB-C, no UART adapter needed. The ESP32S3 and the RP2040 both have native USB. After that, all updates are wireless via ESPHome OTA. And now the most satisfying part: watching it all work. On the front of each module, the status LEDs give you an immediate visual confirmation. Inputs light up when a contact closes. Outputs light up when a relay fires. The M1's front panel OLED shows the DOMIX logo and current time on the home screen. And with the 3 buttons, you can navigate through every module, see live input and output states, and even toggle outputs directly from the cabinet, without touching a phone or a computer. The MQTT topics carry retained state, so the moment a new client connects, it immediately knows the current state of every device. The sensor nodes publish presence, CO2, VOC, temperature, and light every 5 seconds. And the IR transmitter lets you control any infrared device, your air conditioner, your TV, directly via MQTT command. For a typical home, 2 bedrooms, kitchen, living room, bathrooms, garden, you're looking at over 140 inputs and outputs, all managed within a single DOMIX cabinet. The I2C bus capacity is well-defined and predictable. You can plan your entire configuration before you even order the first PCB. That's DOMIX, an open-source, modular, DIN-rail home automation system that you design, build, program, and fully understand. From the first resistor to the last MQTT message, all the schematics, firmware, 3D models, and documentation are available as open source. The full technical documentation is linked in the description, and so is the GitHub repository. DOMIX is licensed under Creative Commons BY-NC-SA 4.0, so feel free to study it, fork it, adapt it, and build your own version. If you found this interesting, please subscribe to the channel. It really does make a difference. Thanks for watching. Thanks again to Oshwalab Stars 2026 for their support, and I'll see you in the next one.